This conference will now be recorded.
Hello everyone. So the topics we are discussing today, types of organic reactions. Under this heading, one type of reaction we have already finished, which is substitution. Here basically we have total 4 types. So first type is already discussed and rest of the 3 types we will finish today, and once it is finished, then we'll start different purification procedures for organic compounds. So substitution reactions, we have seen all these different types: nucleophilic substitution, electrophilic, and free radical. So when the attacking reagent is some nucleophile, the corresponding substitution is nucleophilic. When it is electrophile, electron deficient species, and when there is some free radical reagent, for example, R, any species, any reagent with a dot, that means single electron. Fine. So all these 3 types of substitution we have seen. Next we will start addition reaction. So just like substitution, here also we have 3 types. But what is addition? As the name suggests, addition. So here 2 species will combine together and you will get some new species. So two species will be added to each other. That means these 2 species will be combined. So it is a characteristic reaction of unsaturated compound. Remember, addition reactions, it is possible only when there is some unsaturation. It may be CC double bond, it may be CC triple bond, it may be C double bond O, and other types of unsaturation, because these are the most common. So I have just drawn these 3. While localized double bonds or triple bonds are present. Localized double bonds or triple bonds, try to understand the meaning. If it is not undergoing in resonance with some adjacent double bond or with some adjacent negative charge, then it is localized. So suppose I am drawing CC double bond like this, and then just adjacent to it we have some negative charge over oxygen. Now this double bond, it is not localized because this type of resonance will be present, and as a result the position of this double bond is not fixed, right? So it must be localized double bond or triple bond, not just unsaturation, it must be localized also, free from any resonance. So if we have this type of unsaturation, then in presence of some suitable reagents, now these reagents may be nucleophile, it may be electrophile, or it may be free radical. Now in addition reaction, what happens? One pi bond will be broken and 2 new sigma bonds will be formed. So let's, for example, if I am taking simply CC double bond, here one sigma bond is present and one pi bond is present. Now out of this sigma and pi is compared to sigma, it is weak bond. So this bond will be broken, and when this bond will be broken, what will happen? Now these 2 carbon valency will have to satisfy. Now from the reagent, 2 parts will be coming. Suppose in the reagent, if it is of this type of form, A and B, now what will happen? One bond will be with A, another bond will be with B. So here an important point to notice is that one pi bond is broken. So this pi bond is broken and you are getting 2 new sigma bonds. So this is new sigma bond, this is new sigma bond, this is old sigma bond. It is still intact. Okay, but these 2 are newly generated sigma bond. So this type of effect we will see in addition reactions. And if it is, suppose instead of CC double bond, if you have started with C double bond O, then also same type of observation. So here one sigma bond, one pi bond, the pi bond will still be intact, but sigma bond will still be intact, but 2 new sigma bond will be generated. Okay, so in this way, mostly this B you will see it is hydrogen which will be added to oxygen. So we will see the examples under each of these heading: nucleophilic, electrophilic, and free radical addition. So we'll start with nucleophilic addition. So first I'll show the examples with some general molecule, and then actual examples we will see. So when it is nucleophilic addition, now under this heading, what we can get? Suppose we have bond between A and B, A double bond B. This is the unsaturation, and you are treating it with some reagent which is YW. Now in this case, what will happen? As it is nucleophile, now if you are thinking where from the nucleophile will come. So basically what will happen, from this YW, the nucleophile will be generated. So in this YW, suppose Y is more electronegative. So negative charge you can expect on this, right? So what will happen? The attack will be, see, you can actually, as I am showing it with some general structure, it may be, at a first glance it may seem some difficult, you may feel some difficulty, but when you will actually see the examples, it will be clear to you. So here Y is basically the attacking reagent, which will be drawn towards this pi bond. So the attacking reagent is electron rich. And when it is attacking like this, now there will be bond formation between B and Y. And what is the fate of W? W will carry some positive charge because Y has taken both the electrons with it. Fine. Now in this case, we are treating AB with some molecule YW, but this may be directly any charge containing species. For example, it may be directly any charge containing species like Cn minus, but I am showing it with neutral molecule. And when this attack will take place, there will be negative charge over A. Now ultimately this A and W will connect to each other, and the final molecule we are getting like this. So here these two are the newly generated sigma bond, and pi bond is already broken. Now we will see the actual examples for this type of nucleophilic addition. Now remember, nucleophilic additions are very common for carbonyl compounds. It may be aldehyde or it may be ketone, but C double bond O, whenever this group is present, it will be drawn towards nucleophiles. Why? Because see here, carbon and oxygen, if you compare electronegativity, oxygen is more electronegative. So partial negative charge will always be over oxygen compared to carbon. That is expected. Now, when there is some accumulation of positive charge over carbon, what will happen? Nucleophiles will be attracted towards this carbon. So that is the reason nucleophilic additions are very common when you have some carbonyl compounds. Now, these carbonyl compounds may be aldehyde, may be ketone, it may be some other that is acid, ester, etc. But mostly we see the examples from ketone. Here I will take ketone and aldehyde. This aldehyde I will take, which is acetaldehyde, CH3CHO. Now, if you are treating it with HCl, now see, HCl you can compare as if it is YW. Now, in this case, the actual portion which will be acting as nucleophile is basically the CN part, that is the cyano part. And this reaction will be assisted by if you have some alkaline medium, because this alkaline medium will help to remove this H, because HO minus is basic. It will capture H plus. So negative charge can be easily generated over Cn. So HO minus, basically alkaline condition, is helping us to generate the nucleophile. So now Cn minus will be generated, and that Cn minus you can also directly show the mechanism like this, but you can also draw Cn minus like this and then attack. Both are okay. So when it is attacking, now negative charge will be coming over oxygen. So what you will be getting? You will be getting CH3, CN, negative charge over oxygen, and here we have H. So here Cn is as if analogous to Y, and W plus is analogous to H plus, which is already with HO. Now ultimately from water, because HO and H together, there will be water. From water it will take proton. And what we are getting finally? We are getting finally OH, HCl. So now try to understand the difference. We have started from this. So this part is the actual part where whatever reaction you are seeing, that is actually happening in this group, right? And here this H is and Cn, these two we have from this reagent HCl, and that is assisted by alkaline medium. So in this case, we are getting nucleophilic addition. Next, we will see electrophilic addition. So this is number one. What about number two? So in electrophilic addition, same type of general way we can draw it. Y, W. Now, as the reagent, from the reagent we will get the electrophile because it is electrophilic addition. This is number one, this is number two. So number two, now it is the reagent will be the electrophile. That means A double bond B, that will be acting as electrophile, because whatever reactions we see in organic chemistry, it is always reaction between electrophile and nucleophile. So in the previous case, YW, from YW, the nucleophile is generated. That is from HCN, the nucleophile CN minus is generated. So here CH3CHO, that is the aldehyde molecule, this part is acting as the electrophilic region. So this part is the electrophilic region where CN minus, the nucleophile, is attacking. Now the reverse case. So in this reverse case, now this will be attacking Y, and as if this negative charge will be broken and negative charge will be over W. And as this attacking is happening, positive charge will be present over A. And bond, sigma bond between B and Y will be formed, and W minus. And finally, we can get AW PY. Now we will see the actual example. Now this type of reactions are common for alkene. So we have taken the simple alkene and we are treating it with HBr. Now here HBr, if you compare with YW, this double bond, that is the pi electron charge, because pi bond will be broken, so that will be attracted towards H plus, and as a result what you will get, now there will be positive charge generated over this carbon, and CH2, now it is basically CH3 because this hydrogen is already taken by it, Br minus. Now this Br minus will attack. So the first attack is where this part is acting as electrophile, and this part is acting as nucleophile, and this part is basically our electrophile, right? And based on this, we are calling this reaction electrophilic addition based on the type of reagent. Finally, this will attack here and we will get addition reaction CH2Br and CH3. I am writing it in this way so that you can understand the actual addition that is happening. So these two atoms are added to CC double bond. So pi bond is broken, sigma bond is intact, right? These two are newly generated sigma. Now the last part, which is free radical, though details of this reaction basically you will get in the hydrocarbon chapter. In hydrocarbon chapter, there will be discussion related to alkenes, alkynes, and there you will see this type of electrophilic additions. Many examples you will be able to see. And the examples of nucleophilic addition, that you will be getting in the aldehyde ketone chapter. Okay, many examples you will be getting because that is very common for carbonyl compounds. It may be aldehyde or ketone. And this type of electrophilic additions are very common where there is CC double bond. Fine. And one free radical example quickly we will see. So again I will take the same ethylene molecule and the reagent is same. See, I have taken again HBr. But what happens? The same reaction if you do in presence of peroxide. So any reagent where peroxide linkage means this type of O linkage. This R group, it may be any group. But this type of peroxide linkage when present and you are treating this CC double bond, that is you are treating alkene with HBr. Now what happens? Anti-addition, that is reverse addition. So in this case what you have seen, Br and H. Now and here mechanism is like that, H plus is first added. But in this case what will happen? Br dot will be added first. So when Br dot is added, there will be dot over this carbon, right? And if you are thinking why Br dot is added, details mechanism basically you will get in alkene chapter, not here. In presence of this type of peroxide reagent, this Br dot is generated from HBr. So, and that Br dot is the actual reagent. So here reagent is free radical. So Br dot is our free radical reagent. This is the first attack. And finally, this molecule will take proton, it is not proton because it is not H plus. Finally, it will take H dot from one HBr molecule and we will get ultimately carbon hydrogen bond. Fine. Though the final product looks same for this reaction and the previous reaction, but this alkene molecule is symmetrical. When you take asymmetric molecule where both sides we do not have same substituents, then you will be able to understand the difference. When you are treating this ethylene with, sorry, ethylene is symmetrical. Suppose you have taken some asymmetric. Suppose instead of CH2, if there is some CH3, CH double bond CH2, then you will be able to understand. Now this Br, whether it will be added to left hand side carbon or right hand side carbon, everything will be decided by the fact whether you are using peroxide or not. But whatever it is, our focus is not on that. Our focus is on, we are trying to understand different types of addition reactions. And we have seen all the three possibilities depending on the type of reagent. So first example we have seen where nucleophile is Cn minus. Electrophilic addition example we have seen where H plus is the electrophile. And the last example where Br dot is the free radical reagent. Okay. So this is a second type of organic reactions. Substitution done, addition done. Now we will move to the third one. Elimination. Addition, the opposite word is elimination. So now you can understand, you just have to do the reverse reaction. So in the previous case, what we have seen, there is some double bond and we have added some reagent. Now what will happen? Two sigma bonds will be broken and there will be generation of pi bond. So that is the difference. If you want to understand the difference with the previous one, this is actually the difference. Okay. So in elimination reaction, these reactions involve the loss of two atom or groups from a molecule, and that will be in presence of suitable reagent, leading to formation of multiple bonds. So as I have said, so you can start with like this. So already there is a sigma bond YW, and if you are removing these two, now there will be generation of a sigma bond, pi bond. Okay. Now, though I am giving this example as a general way, but that depends on what type of elimination you are talking. Okay. The mechanism that I have just shown, it is actually beta elimination. Why? Because the two groups that you have eliminated, that is this atom and this atom, or it may be any groups, that you have eliminated from the positions 1 and 2. You have not eliminated Y and W from the same carbon or same atom. You have removed Y and W from 1 to positions. So that is why it is example of beta elimination. So one by one we will see these three types of elimination. But the common point is it will involve loss of two atoms or groups. Two atoms or groups of atoms from a molecule, and it will be in presence of some suitable reagent. Now here see, we have not mentioned anything that is type of reagent, whether it is nucleophilic or electrophilic or radical. Not based on that we are doing the categorization. The categorization we are doing based on the position of the atoms or groups that you are eliminating. Okay. So when it is alpha elimination, number 1, 2 and 3. So for number 1, that is alpha elimination, so here we will take very common example, which is CHCl3. So in chloroform, what happens? This H is very acidic in nature, and because of these 3 electron withdrawing groups. Now if you are treating it in presence of some basic reagent, what will happen? There will be ultimate removal of HCl. That means here, that is a net reaction I am talking about. Here one H, first H will be removed, then Cl. But net removal is H and Cl. Now this removal of H and Cl, it is happening from a single carbon atom, right? And that is why it is under the heading of alpha elimination. Though it is true that beta elimination is most common. Whenever we talk about elimination, it is the beta elimination that you will see most of the places, not alpha or gamma. But we have to understand the difference among these three. So that is why it is important to discuss all these three, right? So what is happening here? First, this H will be removed and there will be formation of negative charge. Okay. And finally, this one of this chlorine will be removed, and it will be removed in such a way it will take the electron. And after all, there will be generation of carbene. Now this is a term you are seeing something new. This is also a type of free radical. Sorry, this is also a type of reaction intermediate. Remember in last class and also the previous classes we have seen carbocation, carbanion, free radical. So just like that, this is also a reaction intermediate, but details of this is not required in our syllabus. So that is why it is not discussed. But remember, this is also type of reactive intermediate or reaction intermediate. So in carbene, what happens? This type of 2 electrons are extra because see, try to understand the difference between negative charge and lone pair. Lone pair means what? Here carbon has total 4 valence electron that we know. So 2 electron used up for 2 sigma bond formation. 2 electrons are not used up, right? But in this case, it is negative charge. Why? Because out of that is 4 valence electrons, 3 used up and still 2 electrons are there. So when there is some extra electron compared to its valence electrons, then you put negative charge. But in this case, it is different. There is not any extra electron present. So you cannot put negative charge. So remember, in this way, in presence of basic medium, first there is removal of H. You are getting CCl3 with negative charge, and then Cl will be removed, and it will be removed in such a way it will take 2 electron. So now surrounding carbon there is actually, obviously there is 2 more electron, but if we consider the valence electron, carbon is having 4 valence electron. But in this case it is extra. So that is why there is negative charge. Fine. So here carbene is generated when there is alpha elimination of HCl from chloroform in presence of basic medium. This is the first one. Now beta elimination we will see. So here we have CH3, CH2, Br. So in beta elimination, mostly it is very common in haloalkane. That is, halogen will be present in alkane. One of the carbon hydrogen bond, if you replace with bromine, we get haloalkane, right? Here the position of bromine is, if you consider this carbon, it is alpha position. That means this carbon is beta position. So whenever you want to do any beta elimination, there must be presence of atom at beta position that you can remove. Suppose in this case, if there is no beta hydrogen, then how you will remove H and Br? It is not possible. Suppose I am writing the molecule in a different way. I am writing all the hydrogen as if it is Me3C, then CH2, and then Br. Now elimination is not possible because at beta position you do not have any hydrogen. So you must have some beta hydrogen. Mostly, why I am saying hydrogen? Because mostly beta elimination is the elimination of H and halogen. Okay, so here it is not possible. But it is possible in the previous examples. And when you are removing one H from beta and this halogen from alpha, you are getting H2C double bond CH2. So here this sigma bond is broken and one of this carbon hydrogen bond, I am writing it in this way, CH2 and then one carbon hydrogen. You are breaking this sigma bond. So 2 sigma bonds are broken and 1 pi bond is generated. That means here it is leading to the formation of a multiple bond. So this is our multiple bond. Okay. Though it is true that multiple bond, we are saying that, but it is mainly for beta elimination because in the previous example alpha elimination, there is no generation of multiple bond. So it is exclusive for beta elimination only. Now what about the gamma elimination? In gamma elimination, now you have understood the fact. You know now what is alpha because from same carbon, from same position, both hydrogen, halogen removed. Then beta 1 and 2 position. Now obviously it will be 1 and 3 position because gamma means what? 1, 2, 3. Or you can say alpha, beta, gamma. So this is 1, this is 2, this is 3. So if I put 2 bromine at position 1 and 3, you can also call it alpha, beta, gamma. Same thing. 1, 3 elimination or gamma elimination. So if these 2 sigma bonds are broken and in this position a newly generated sigma bond, if you draw, what you are getting? From 1,3-dibromopropane, you are getting now cyclopropane. And this type of reaction occurs in presence of zinc, where zinc will provide some electron and this electron will be attacking this bromine. This sigma bond will be broken and then attack will be from this position to this Br will be removed. So ultimately the byproduct is ZnBr2. Zn is removing, it is helping us to remove both the bromine atoms. So the side product is ZnBr2, and the main product we are getting, it is cyclopropane. So see here also we are not getting any newly generated pi bond. It is also only true for beta elimination, and this is the most common, not the other two. Fine. And the last type. So we have seen substitution, we have seen addition, then the reverse of addition is elimination. Now rearrangement. So in rearrangement, there is nothing we will add, nothing we will be removing, that is nothing we will be eliminating, but there will be some position change for the atom or groups. So in this type of reaction, an atom or group in substrate molecule migrates from one position to another position. So when they are changing their position, some bonds are broken, some newly generated bonds are there. So you will be getting a new product. We will see example. Suppose you have this benzene ring and we have OH group. Sorry, not OH group. Here I will put A star. So O, C double bond O and R. These are maybe any alkyl group. So this is basically phenyl ester. This is a ester. Now in presence of some Lewis acid and heat, what will happen? This hydrogen at ortho position and hydrogen and para position, these two hydrogen, now it will come to the position of COR group. So what I am saying actually, this COR group and this H, if they exchange their position, then you will be getting OH and COR is here. But the same thing is if it is happening with this H and again this one. So OH will be here, but COR will be here. So two different types of product possibilities there. And this is basically orthohydroxy aryl ketone. Why I am writing aryl? Because we exactly do not know what is the type of R. It may be methyl, ethyl. But see, here ketone means what? Both sides of this CO group, we have two different groups. That is this side, this side. Now in our case, this side we have benzene ring, phenyl or substituted phenyl, and this type we have any R group. So that is why I am saying aryl ketone, where one of the group is aryl group. Why aryl? Because there is OH substitution. So I am not saying phenyl ketone. Phenyl means only benzene ring, but here we have OH substituted phenyl ring. That is why in general I am saying aryl ketone. So this is also a ketone, but orthohydroxy substituted aryl ketone. And the second molecule is para-hydroxy substituted aryl ketone. So this is also ketone. That is the second possibility. So this is one side of the carbonyl, this is another side. But this side we have OH substituted phenyl. So that is why it is aryl ketone. Example of aryl ketone, but it is para-hydroxy aryl ketone. So this is one example. Another example is RC double bond N OH R prime. Suppose two R groups different. Now this molecule is known as ketoxin because this is generated from keto. Keto is C double bond O R prime. Now instead of this C double bond O, if you have this NOH, it is called ketoxin. In presence of H plus, there will be some change of position of the atoms. Now in presence of H plus, what will happen? In between this carbon and R prime, now nitrogen will come. Fine. And this oxygen, now it will be forming bond with carbon. So what we will be getting? Oxygen will come in the position of nitrogen, N will be coming in between C and R, and hydrogen will be attached with N. So we will get R, C, double bond O, N, H, R prime. So this molecule is basically amide. Amide means when you have CONH group, that is called amide. And if it is this R prime is also H, it is primary amide. If it is alkyl group, it is secondary. But whatever it is amide. So from ketoxene, now you are getting amide, and simply because of some atoms are changing their positions. That is why we are getting this. So these two are the examples of rearrangement reactions. So all the types of reactions we have covered. That is the 4 types. Next we will start methods of purification of organic compounds. Now under this heading, you can see total 5 methods, right? So why it is important? Why we need to purify organic compounds? Suppose you want to study the structure, physical properties, chemical properties, biological properties of a particular organic compound. But to do that study, it must be pure. You cannot do all this study with impure compound. Then your result, experimental results will be wrong and you will reach some wrong conclusion, right? So that is why it must be pure. And it must be pure means you have to purify it. And there is several methods following which you can do this purification. Now, if you are thinking why there is so many methods, because that depends on what type of compounds, organic compounds you have that you want to purify. So it depends on not just on the type of organic compounds, but also what kind of impurity you have, right? So the nature of impurity, you have to keep that in mind. Also the nature of organic compound. So based on these two factors, we have to apply any of these methods. Now, nature of organic compound means what I'm trying to say. It may be liquid, it may be gas, it may be solid. So many different physical states possible. Then it may be polar in nature, high dipole moment. It may be non-polar in nature. It may be very volatile liquid. It may be very high boiling point liquid. Sometimes it may be solid. Okay, so these are the different types of when you are talking about the nature of the organic compound that you want to purify. And nature of impurity, that is also important. Suppose your impurity is water soluble, then one type of method you will apply. Suppose your impurity is very high boiling, then you have to apply something else. So these are the different things based on which we have to decide which method is suitable. Okay. So first method is sublimation. Now what is sublimation? When we are talking about sublimation means we know when we are boiling a liquid, then from liquid state it goes to gaseous state. Then when we are melting something solid to liquid. But suppose you are heating some solid and directly it is going to gaseous state rather than first going to liquid then gaseous. Suppose directly it is going to gaseous state. Then that is called sublimation, and this method is only applicable for that type of substance. So there are some solid substances. You can see some examples: benzoic acid, naphthalene, camphor. Those are sublimable. Sublimable means where sublimation is possible. So when you are heating all these solid compounds from solid state, directly it goes to vapor state without any melting. So that is why I am saying they are sublimable. That is their property. And when you are cooling the vapors, you will get back the solid. And that reverse method is deposition. Fine. So here you can see this picture. Suppose we have any solid, you are doing sublimation, you are applying heat, and you are directly getting gas. And the reverse process, when you are cooling it, you are getting solid again, and that is basically deposition. Fine. Now this method is useful only in the purification of such solids and are associated with non-volatile impurities. Why the impurities must be non-volatile? See, few minutes ago I was just saying that nature of impurity and nature of organic compounds both are important when you are deciding which purification method is to use. So see, here also we are seeing the same thing. For sublimation, first of all, the compound must be sublimable, otherwise no question of sublimation. Second point is your impurity non-volatile? Because if your impurity is having some volatile nature and when you are heating the solid, then with this gas you will also get the non-volatile impurity. So that is why impurity must be non-volatile, so that when you are heating it in the vapor, you get only your desired compound, not the volatile impurity. So that is why it is mentioned clearly that your impurity must be non-volatile in nature. Okay. Now we can see the picture. So here we are doing this, though here example is with some inorganic compound, but it is also true for any of these examples. But whatever it is, technique is same, whether you take inorganic or organic. So cotton plug, we first of all, we have this inverted funnel that you can see. This is inverted funnel. We have taken the sample or the compound that you want to purify in a petri dish or china dish type of container, where we have this mixture of ammonium chloride and salt. So suppose this is one compound which is sublimable, NH4Cl, and plus salt. So salt, suppose we have sodium chloride. Now these two mixtures are present and you have to purify it. Now this is sublimable, not NaCl, and it is not also volatile. So all the conditions are fulfilled. So we can apply sublimation method. And you are now applying heat. There will be generation of vapor of ammonium chloride. And when it will come to the surface of this cool surface of this inverted funnel, because here the temperature, and obviously in this region the temperature, there is difference. Sometimes there is some wet filter paper also you can put here just to make the surface cool. But here this vapor, it will come to this cold surface of, that is comparatively cold surface of this funnel, and it will be solidified to this pure compound. So in this way we can remove the impurity, the non-volatile impurity. You can suppose you have camphor and it is mixed with some salt, then instead of NH4Cl, now you will have camphor plus NaCl, and you are doing the same method. Then in this region you will get some solidified camphor. Okay. Next method is crystallization. So in crystallization, first of all, what is crystal? And this method is obviously for solid, because whenever we are talking about crystal, that is for solid state. In the previous method also for solid, not just solid, sublimable solid. This method is also for solid. So crystals are the purest form of substance. Not in all solid you get crystals. It is only for some solid compounds where crystal nature is present, because these substances, they are having some definite geometrical shapes, and that is why we have crystals. But what is crystallization? The process by which impure compound is converted into its crystal is known as crystallization. Now for solid organic compounds, this is the most widely used method. Because if you consider the previous method, it is good, it is easy to do, but it is not necessary that you will always get some sublimable type of solid compound. Then what to do? If it is not sublimable, but if it is having some crystal nature, you can do crystallization. So that is, it is the most widely used method. Okay. So the impure compound, first it is dissolved in some suitable solvent. Now when I'm saying suitable solvent, there is different way we can choose which solvent is perfect, and we'll discuss this under the heading of selection of solvent. But here we are just saying the term suitable solvent, in which we will take this impure organic compound first. And remember, this solvent, when we are dissolving it, it should not be very soluble, because if it is very soluble, then that is at room temperature. Suppose you are dissolving in some solvent and quickly it is soluble, then it will not work, because if it is very, its solubility is very good, what will happen? Crystals will not come out easily. So it is better if it is not so easily soluble, it is sparingly soluble at room temperature condition. But if you are providing heat, then it is having some appreciable solubility. So if this type of situation is present, then we can say it is a suitable solvent. Okay. Then the solution is concentrated to get nearly a saturated solution. Now, I will not say that this is always necessary. It depends on the nature of compound and also what is the concentration of the solution. Suppose if it is very dilute, sometimes it will be necessary uh, to make it more saturated, because the more it will be towards saturation, that is just easily you can get the crystals when it is cool, right? So if it is very dilute, then sometimes it is required to make it saturated. And if it happens that it is easily soluble at room temperature, then also saturation you have to do, because it is easily soluble at room temperature means what? You have to increase the possibility of crystallization. So you have to make it more saturated. Fine. So it depends whether you have to heat it more so that you can get a saturated solution and easily get the crystals of pure substances. Now, once you get the crystals, you can remove it by filtration. Okay. And then you have to clean the crystals with some solvent in which it is not at all soluble, and finally you have to dry it. And the filtrate that is remaining, which we call mother liquor, that will be having this impurity present in it, because impurities are not in the crystals are pure, so impurities will be remaining in the left out mother liquor. And there may be a small amount of the dessert compound also. It is not that all the compounds will be in the crystal form. Some amount may still be present in the mother liquor. So if this quantity is not small, suppose still there is some, if you are thinking large amount of compound is still present, sometimes we need to do recrystallization of that mother liquor. So again, the mother liquor you have to make it saturated, that is dilution must be less, and you have to repeat the process. So if it is small quantity, it is okay. If it is large quantity, recrystallization is required. Okay. So for crystallization, one by one, all the steps we will see. So the first step for crystallization is you have to choose the solvent properly. Now, it goes without saying that the solvent should not react chemically with the impure organic compound that you want to purify, because if there is some chemical reaction occurring, your purpose will not be fulfilled, right? So this must be the condition. The solvent should not react. Then the solvent should dissolve more of the substance upon heating than at room temperature. So this point we have already seen in the last slide. So it is because so that the excess of substances can be removed upon cooling. Because if it is at room temperature easily soluble, then if you are cooling it, it will, that is, you are heating it, then cooling it, then again it is at room temperature, crystals will not come out, because at room temperature it is already soluble condition. So how crystals will be there? But if it is better, if at room temperature it is not having very good solubility, still you can see some solid, and then you are heating it and you are getting some clear solution. Now you are keeping the, you are waiting so that it can come at room temperature, and then you can see crystals. Either the impurities should not dissolve at all in the solvent, that is one condition, or if they dissolve, they should be soluble to such an extent that they remain in the solution only. So for impurities, two things may happen. Suppose the impurities that you want to remove, that is not at all soluble in solvent. Now if it happens, it is not at all soluble, then just before crystallization you can do the filtration to remove the impurity as solid. That is one condition. But if they are soluble, if they dissolve, the solubility should be such that they remain in the solution only. So it is the second condition, means when impurity is also soluble and your desired compound is also soluble. But when you are cooling it after heating, then you will be getting only the pure compound, that is only the desired compound, not the impurity. So solubility should be such. To such an extent, they remain in the solution only. So their solubility should be basically good in the second case. That is in the mother liquor part that is left upon crystallization. In the mother liquor, they should remain, not in the crystal. if the compound is highly soluble in one solvent. Suppose you are not getting a solvent which can fulfill this condition. That is at room temperature not sparingly soluble, and when you are heating it is good, it is perfectly soluble. Suppose you are not getting that condition. Another way is there, and solution is that if the compound is suppose highly soluble in one solvent at room temperature, so you don't have to heat it, then what to do? But because this condition we don't want, then what you can do, suppose it is very highly soluble in one solvent but not very soluble in another second solvent, then you can use mixture of these two solvents. So in that case, crystallization you can be carried out in a mixture of these solvents taken in a suitable ratio. So what happens, suppose you have taken some solvent, you are putting your sample, and it is completely soluble, it is transparent solution. Now another solvent, this is solvent 1. Now another solvent number 2, if you add it dropwise, and you are adding this second solvent in such a way that suddenly you can see some turbidity. That means it is a proof that it is not very soluble in the second solvent. So that is another way we can do two solvent suitable ratio we can take. Now the important question, what are the solvents that are most commonly used? See, what are alcohol, chloroform, benzene, acetone, ethyl acetate, petroleum ether? All these solvents are used for this purpose. Once the solution is chosen, you have to prepare the solution. That is, once the solvent is chosen, you have to now prepare the solution. So preparation for solution, the organic substance is dissolved in minimum quantity of suitable solvent. So don't make the solution very dilute, it should be as minimum as possible. If by chance you have added many high amount of solvent, you have to heat it and make it concentrated, that is increase the concentration. Now in some cases, if you know that the impurity, that is your compound, you are expecting it should be white, it should be clear, but you are seeing some color. So what to do? Sometimes charcoal can be used to remove the color impurity. So in that case, if you already know that your compound should be white and you are seeing some colored substance, you can use a small amount of charcoal, which is nothing but carbon, and it has the capacity to absorb the impurity on its surface. So what we do, we add some charcoal to this previously made solution and heat it. Then you will be clearly seeing there is some decolorization happening. If it is only for if any color impurity is present, it is not mandatory, right? And then you are heating it over a wire gauge or water bath. Water bath is mostly used if it is having a low boiling point, so that low amount of heat you are providing. And that depends on the boiling point of the solvent. Low boiling solvent, water bath is better. High boiling solvent, directly you can use fire or wire gauge. Okay. So we are heating it, then decolorization will be happening. Now charcoal is solid and you have to filter it. Before cooling, whatever you will do, first of all, as you have added, when you are adding charcoal, you have to filter it. It is only for that case where you have added charcoal. So filtration of hot solution you have to do. So you have added charcoal, you have heated it, and then you have to do the filtration to remove this charcoal carbon. The hard solution so obtained, it filtered immediately through a fluted filter paper placed over a funnel. Now what is fluted? Normal filter paper is okay, but what is fluted? Fluted is basically the normal filter paper. It is made from normal filter paper and it looks something like this. So when you take normal filter paper, it is close to the surface of this funnel. But when it is fluted, you have given it this type of shape by pressing the paper, and there is a technique for that. Now what happens, the surface area is highly increased, and also it is not directly, that is close to the surface of the glass surface of funnel. So as a result, what will happen, when we want the filtration to be very quick, so when you use fluted filter paper, the filtration happens very quickly. The first reason is here surface area is increased, when you have taken this type of shape filter paper. And the second reason is, as these surfaces are not directly adhering to the surface of the glass, so what will happen, the filtration process will be very quick, and that we want. Okay, so that it still remain hot, because if it takes time, there may be some cooling already happening, and crystallization will start, that can mix with the charcoal, that we do not want. So we want the hot solution to be quickly to be filtered, and that is why you have to use this fluted filter paper. Fine. Finally, this hot filtered, you have to allow it to cool undisturbed. You should not disturb it, otherwise crystallization will be hampered and crystals will begin to separate. So remember, this filtration process, it is only for when you have used some charcoal. Now when you are cooling it, crystals will separate out, but sometimes it may happen you are not seeing any crystals even after a long time. So in that case, you can do two things. One thing you can do, it can be induced either by scratching the walls of the container. So suppose you have taken a test tube, and in that you have kept this solvent, you have kept this solution, but it is not any crystals are not appearing. Then what you can take some glass rod and you can scratch this wall of the container. So here I have drawn test tube. You can scratch the walls of the container, or you can add a few crystals of pure compound. Suppose you already have some sample of the pure compound which you are basically purifying. Suppose you are purifying benzoic acid. For example, I am saying you already have some pure sample. Then what you can do, you can add a few crystals of this pure compound which you are actually purifying to this solution, and that will help in the crystallization process, and this is known as seeding. Okay, so in this way we can do crystallization, and once crystals are appearing, that is crystals begin to separate, then you have to do another filtration. So final stage is you have to isolate it, and then you have to dry the crystals. So once the crystallization process is complete, crystals are separated by filtration under reduced pressure using Buchner funnel. So this is a specially designed funnel. It is not like normal funnel. In Buchner funnel, what happens? You can apply some pressure, so it will suck the filtrate. It will help in quick filtration. So crystals that are already in the filtered paper, you can wash it with some small quantity of pure cold solvent. Cold solvent, why? Because if you use normal temperature solvent, there is a chance that the crystals will be dissolved in that solvent. But if you use cold solvent, that means low temperature, so it will not be dissolved. Then crystals are dried either in air, that is normal air, if you just spread the crystals, and with time it may be dry, or you can place it in steam oven or an air oven. Now that depends on what is the melting point of the solid that you are purifying. Because if it is very low melting, there is no point of keeping it in steam oven, otherwise it will be melted, right? In that case, a plain air is okay. You are just drying it open air. But if you know that it has having very high melting point, then oven can be used, air oven or oven. So here we have this picture. So see, suppose this is the desert compound, dot sign black, and the square sign, this is the impurity, soluble impurity. Because if the impurity is already insoluble, then it will be easy thing for us, because then at a first step you can do the filtration. But when the impurity is soluble, then this question arises. So you have some impure solid. Look at the sign of these two. Then you are adding solvent, you are heating it, and it is already dissolved. Now we are cooling it, some crystals are appearing, and look at the impurity, they are still in the mother liquor, though some amount of desert compound can be there. Then we are using this Buchner funnel where suction filtration we do. So in suction filtration, here you can see this outlet. So in this position outlet, actually we that is pressure is applied, that is some vacuum is created inside, some vacuum is created, and as a result the filtrate that is easily accumulated inside the container, and you are getting your desired pure organic compound in this funnel. So Buchner funnel, it looks like this, and here you can place your filter paper. So it is specially designed because you are applying some pressure, some vacuum is generated. So obviously this funnel is having some different design compared to normal funnel. So in the mother layer, you can see soluble impurities. These are the signs. So some amount of desired compound may also be present. But if this desired compound you are seeing its amount is very high, you have to do another crystallization, and that is known as recrystallization. Fine. Crystallization part we have finished. So next method we will not start it today. The next method is differential extraction, that will start in the next class. We are ending the session here. Thank you for listening.